So in this example, we're going to see how to solve the differential equation x dy minus y dx minus the square root of x squared minus y squared dx equal to 0. And in this playlist, we're dealing with homogeneous differential equations. So in this case, we want to test this first to see if it is homogeneous, and if so, to what degree. So we can test for this as follows. To do this test, we simply substitute lambda x and lambda y for the x and y variables. So for our equation, this is what we get when we do that. Again, replacing x with lambda x and y with lambda y. And when we reduce this and factor out, we see pretty quickly that we can factor a lambda out from the entire equation. And what's left in the brackets then is our original f of x and y. So this tells us that this is a homogeneous equation, and it has the degree of 1 because we have lambda to the first power as our factor that comes out when we put in lambda x, lambda y. So since this is a homogeneous equation of degree 1, we'll now use the standard transformation where we'll let y equal to vx, which means that our dy from the chain rule will be v dx plus x dv. So when we do this, we can substitute this in, and then for simplicity, we're going to divide through by x, and this will transform our equation then into v dx plus x dv minus v dx minus 1 minus v squared square root dx. But we see right away that we have a plus v dx and a minus v dx, so we can reduce this a little bit further to x dv minus square root of 1 minus v squared dx equals 0. So this gets us back to the separation of variables part of the problem. So we recall that if we have something in the form of some function of x times some function of v dx plus some function of x times some function of v dv, that by inspection we should be able to determine an integrating factor such that it'll reduce our equation to this form. This form's important because we see now that we have one term all in x, one term all in v, and so this is what's meant by separation of variables. So for our transformed equation, which is shown above here, we can define our f2 as x and our g2 as square root of 1 minus v squared. So this would then give us a resulting integrating factor of x times square root of 1 minus v squared. And when we apply that to our equation, the result is what's shown here, v over square root of 1 minus v squared minus dx over x equals 0. So with this equation in this form, we can now integrate directly term by term. And remember, for completeness, we're integrating the 0 as we assume that that comes from some constant that we could determine if we had boundary conditions, but we don't. So when we integrate this term by term, we end up with arc sine v minus natural log x equals to some constant. And again, the arc sine, this is the defined integral for this from any integrated integral table. And of course, 1 over x always is natural log of x. So we can make use of natural log relationships and get the following. Arc sine v minus natural log x equal to some constant. And combining terms and using natural log rules, we come up with this final equation. But we need to remember that this is just the solution to our transformed equation. We want to get back to our original equation with the original variables, so we'll have to transform this back. So we recall that we did our transform by setting y equals to vx. So in order to transform it back, we're going to have to substitute or solve for v, which gives us y over x. So we can substitute that back into our original equation, which gives us this. And then we can take the exponential of each side, and this gives us our general solution to the original equation, which is an x and y of e arc sine y over x equal to some constant times x.